The first two things, there's going to be a quiz on Wednesday. I know I've said this before, but this time I mean it. So quiz 2 is going to be on Wednesday. And remember, these are cumulative, so this can be questions from any of the lectures anywhere in the class. It's not calculations, it's just short answer questions about what I said in class. So, just go back and read, skim your notes, that kind of thing. And then exam 3 is a week from Wednesday. And that is going to be up through stresses and beams. And just like with the quizzes, all the other exams, be ready for, old questions too, stuff on old things. I do, in this class, it's kind of possible to keep bringing up old stuff as you go to new stuff, so like, for the most part, you keep sort of doing the old stuff as we go to the new stuff, like I'll ask you to draw stress cubes and do principal stress tensors and find stress tensors with maximum shear, and all that stuff is like the old stuff. But I would say at least glance back at the old problems to make sure that you're not forgetting how to do anything. All right, so here's number 5. And it was number 5 in intro. Oh, in intro. Okay. That's good for you because that one's hard. Oh, this is way better. All right, so first you have to calculate the internal loads, and then we have to do some thinking about where to analyze the stress tensor and then calculate the stress tensor using the stuff we've been doing. So to calculate the internal loads, first we have to calculate the external loads. At the fixed joint, we have this unknown force vector, I'll call that R, and then we have an unknown couple, I'll call that MR for reaction moment. And then we have our distributed load. Now that I've chosen the body to isolate, I can represent that as a point force. So the centroid is a third of the way from the edge to the point. So it's over here. The total length of the beam is 1.5. So the total force is 1.5 times 10,000 divided by 2. So I think that's 7,500. And that's all that's going on there. So Newton's second law says Rx, Ry plus 0, negative 7,500 is equal to zeros. So R is equal to 0, positive 7,500. And then the moment equation about the z-axis. I'll put my about point here. So we add on the couple, and then we have a moment arm of, this is 1.5. This 7,500 is a third of the way from the right end to the left end. So that's a moment arm of 1, a force of 7,500. Would that make it rotate clockwise or counterclockwise around the about point? Clockwise, so we want the negative. And so that reaction couple is equal to positive 7,500. Now we can calculate the internal loads. How many cuts do we need for this? Just one, that's right. So this cut represents everything from 0 to 1.5. And I guess I didn't really make that look like a cut. We're not going to go all the way. Yeah, question?
Yeah, on the weight, you say it was 1.5 times 10,000 over 2, right?
Yeah.
100. Why on the rotational second law we multiply just by 1? Shouldn't be 1.5 also?
Okay, yes. Because remember that when you calculate, so I kind of skip the step that I do a lot of times. When I go from representing it as a distributed load to a point force, remember the way you do that is draw out the shape. We have a width of 1.5 and a height of 10,000. Okay. And when we represent this as a point force, it's going to act at the centroid of this shape. And the centroid of this shape is, 1/3 of the way from the edge to the point. So that means it's 2/3 of the way from the point towards the edge. And so this distance is 2/3 of 1.5, which is 1. So that's how. And then the magnitude of the point force is the area. So that's 1.5 times 10,000 over 2. Okay. All right. So now our cut. So we have the 7,500 up. We have the couple here of 7,500. Then we have, I'm going to do this in 2 steps. So we have this part of the distributed load. And I'll think about the height of that in a second. Then we have T, V, and M. You could put in the fancy T for torque, but there are no external torques, so that's going to end up being 0. So I'll just draw it like this. Okay, what about the height of this? So we know that the length of this cut is X. So what's the height of that triangle as a function of X? This continues until the end of the beam, and it would be 10,000 here, but you can see that it's not to 10,000 when we get to this value X. So we need to represent that height using the function, the equation for the line. Okay, so the equation for the line here, you can think of this as y equals mx plus b. When x is equal to 0 at the wall, the height is 0, so b is equal to 0. That's easy. And then m is the rise over the run. So it rises from a distributed load of 0 to a height of 10,000 over a run of 1.5. So that is 6.6 repeating 1,000. And so the function for that line is 6.6 repeating. This is 1,000. So 6,666.6 repeating. And so that's what this is. And so that is what the height of this distributed load is at this right end at the value x. And now that we have that, now we can represent this as a point force. We have a right triangle with a height of 6,666.6 repeating times x. We have a width of x. The centroid is 2/3 of the way from the point to the edge. Well, the whole thing is x, so that just means this is 2/3 x. The area is the base times the height divided by 2. And so that's 3,333.3 repeating x squared. And so now I'll redraw this free body diagram. So we have this force of 3,333.3 repeating x squared. And we have an upward force of 7,500 and a couple of 7,500. And then our internal loads. Okay. Any questions up to here? What about the distances? Well, the distance to this is 2x over 3, and the distance to the end is x. And we'll use those when we calculate our moments. So Newton's second law says 0, 7,500 plus 0, negative 3,333.3 repeating x squared plus t negative v is equal to zeros. So t is 0. V is negative 3,333.3 repeating x squared plus 7,500. And then we'll go to the moment equation. This is about the z-axis, and our about point is here. So we have the couple of 7,500. Then we have a moment arm of 2x over 3 with a force of 3,333.3 repeating x squared. And is that a clockwise or counterclockwise moment? Clockwise, so we want the negative. And then we have plus m minus vx is equal to 0. So m is equal to, so So we have 2222.2 repeating x cubed. And then we have plus Vx, which is minus 3333.3 repeating x cubed plus 7500 x. And so then the bending moment is negative 1111.1 repeating x cubed plus 7500 x. Yes.
You chose negative there because it was clockwise or counterclockwise?
I chose negative because it was clockwise about that.
What about the movement from the fixed joints? Is there like a constant or something like that?
Oh, I forgot that?
Yeah.
Oh, thank you. Yes, that's important.
It's starting to, if you have it on the left side, it just says
Oh.
it's not on the final equation and circle them up.
Okay. Yes. Don't skip anything. That's a rule. Okay, so we got that. And then add on 7,500 here. I know, I always know I did something wrong when like 5 hands go up at once.
Those shouldn't be negative.
It should. Okay. I'm just making sure you're all paying attention. All right. Any other questions?
Should the 222.2 x cubed be negative right above your answer? So then,
Isn't it was the
Oh, it's positive here because then I moved everything to the right side of the equation. So it's negative, and then it became positive when I got m by itself.
shouldn't when you move the VX over, should that be positive then?
Vx should be positive, so it's positive Vx, but then when you plug in V, it's a negative 3,000 thing. So I think this looks all right to me. Okay, so now we have our internal loads. And in order to figure out, like, what it asks us to do next is calculate the greatest absolute value of normal stress for this beam in the x direction. Well,
Would that just be where the most amount of force from the distributed load, which so at the end, 0.5 meters?
well, let's graph these out and just get a visual sense of what those internal loads look like. Okay, so so the tension is 0, right? That doesn't come into anything. The bending moment looks like, so it's going to start at negative 7,500. And it's going to end at 0. And it is going to be a negative cubic function that looks, so it's going to look something like this. Okay, so if we're just thinking about the stresses due to the bending moment, it's clear that that's going to be as you approach the wall on the left side. And then if we're thinking about the shear force, well, one thing here is, so this is asking us what's the greatest absolute value of the normal stress in the x direction. the shear force doesn't produce any normal stress in the x direction. So really, for what this is asking, we don't even care about what the shear force is. But it would look like it would start at positive 7,500. And it would end at 0, and it would be concave down. Yeah. So again, the shear force magnitude is biggest as you approach the wall too. So the good news is it's very clear what x value we want to look at. So the x value we're concerned about is clear. And that is x equals 0. And, when we calculate those internal loads, we don't actually know what the value is at 0. So I don't know. Somebody remind me in your math classes, how did your professors tell you whether you are approaching something from the positive side, the negative side? Remember that stuff? Like this? So I don't remember. Is that it? Okay. Okay. So we're talking about getting closer and closer to the wall. We never quite get there, but we're basically concerned at the wall. And there's no internal tension or compression. So the only thing that affects the x normal stress is the bending moment. So we're just going straight to the stress due to the bending moment. So we know that sigma xx is equal to negative my over I. We're told that this is a circular cross-section with a radius of 0.02. So I is equal to, so is this pi over 4 times the radius to the 4th? Is that right? Okay, pi over 4 times 0.02 to the 4th. Yeah. So that's 1.257 times 10 to the minus 7. And then, okay, the cross section looks like this. So notice that this stress that we're worried about is linear with y, right? So all we're going to do is basically we're going to calculate this m. We already calculated this I, and then we're going to multiply it by the height above that neutral axis. And notice if we go below, it's symmetric, so we can go just as far below as we can go above the neutral axis. So it doesn't matter which one of those we pick. All it's going to change is the sign. Okay. Sometimes the sign of this does matter if you also have a tension compression to worry about. If you go, say, above the neutral axis, the bending moment is going to counteract the effect of the tension compression. If you go below, it's going to add to the effect of the tension compression. But we don't have that here because we don't have any tension compression. So it doesn't matter which one we choose. I guess I'll choose above, but it doesn't make any difference. So we're worried about this point when x is equal to 0. And at this point, our y is equal to 1 times the radius, so 0.02. Our m at x equals 0 is negative 7,500. So sigma xx is equal to negative of negative 7,500 times y divided by 1.257 times 10 to the minus 7. And oh my goodness. And you get a value of 1.194 times 10 to the 9th pascals. So there's nothing you can do about this. This thing is not staying up. I mean, really what that means is that the smallness of the radius that we chose to design this with isn't going to do it. And we have to beef up the radius of this beam if we want to support an external load like that. Any questions about that?
Wait, how do you know y was, so for a circular, is y just always the very?
Well, what y means is how far above the neutral axis you are.
Yes,
and
then how do you know?
And so since this is a circle, if you're going from the center to here, that's like the definition of the radius.
Oh,
Any other questions? Okay, so now we're going to get to the last type of stress. Ouch. Ouch. And that is the stress tensor due to torque. Okay, so for each one of these, what's the first thing that we've done? So we talked.
on the internal loads.
So like when I first introduced each one of these topics, the first thing in your notes under each one is beam restrictions. So we have to think about under what conditions our calculations are going to work. Well, let me draw what we're talking about now, first of all. So if we have a beam like this, and you have a couple going that way and a couple going this way, this one is a torque T like this, and this one is a torque T like this. And so that's what we're talking about, this twisting couple. So the beam requirements here are very stringent again. We can only do first round cross sections, circular cross sections. Or the only other option is thin-walled closed tubes. Well, this you wouldn't have thought of in a million years, that this would be an option. And this is something that comes up in engineering a fair amount, so this is pretty helpful. And so round cross sections, you could do solid circular cross sections, or you could do hollow circular cross sections. Either one of those are fine. thin-walled closed tubes are like, we could do cross-sections like this, cross-sections like this. We can't do this though. So say you have this triangular shape again. Except this time it doesn't connect. That's not closed, and so we can't do those. And we'll have a different calculation for each of these two types. Okay, so I have a question before we get into doing these calculations. If I wanted to make a problem for you, like a deluxe model problem, where I wanted the total stress tensor to involve the stress due to tension compression, the stress due to bending moment, the stress due to shear force, and the stress due to torque, there's only one shape that works for all of those. Can anyone think what that would be? Circular comes pretty close, but it's not circular. Which one doesn't circular work for? Shear force. Yes. So remember, for shear force, we can calculate the stress along the neutral axis, but we can't calculate the stress for any other point on that cross section. Okay. So there's a whole, almost the whole cross section, we're not able to calculate the stress due to shear force. What one can we do for all of them? We could do it for a rectangular thin-walled cross section. See, say it louder. So this is like our deluxe model. So if you ever on a test or something see me say that the cross section is a rectangular thin-walled, shape, then just go ahead and let your heart just sink, because you're going to have all this work to do after that, But this is our this is like our winner. But why is that a useful cross section? Because you get a pretty good area moment of inertia. So it's pretty good at withstanding moments and things without a ton of weight, because you've taken all the weight out of the middle. So you'll see cross sections like this pretty often in engineering applications. Okay, so now there's always, when you think about these, a little bit of intuition going on. So let's go back to what we're talking about here. So let's say that our internal torque is positive. Okay, so our fancy T is this way. And if you use the right-hand rule to think about the direction of that moment, it means that we have a couple this way, and to stay in static equilibrium, we have to have an equal and opposite couple that way. Okay. And now let's think about what stress element we're going to get from something like this. And we're going to think about it in terms of deformations. Okay? So if before you applied these torques to it, let's think about an element like this. Okay. So like think about it on the surface of this this beam. How is that, like you could imagine just drawing that in marker on the outside. How is that marker shape going to deform when you apply those torques? It's going to it's actually going to change angles. Can you think of that? Like, so you can think of this point as staying where it is, but this one will go down here. This one will go down here. So you'll end up with a shape like that. Okay. That's a shear strain. And what kind of shear stress do you need to create a shear strain like that? Well, you would need this to go down, which means this would go this way. And then you'd have this up, and then this way. Okay. So if you think about it in terms of deformation, what we can figure out here is that a positive internal torque T leads to, think about the signs of, think about the coordinate axes here. This leads to a negative tau x, y. Because our x-axis is this way, our z-axis is this way, and our y is this way. So this downward traction component that I've drawn is on the positive x face in the negative y direction. Okay, well,
And what are the other two?
they'd be 0. Yeah. So this is the only stress component that we get. And I want you to just be aware of something that's coming down the path pretty soon is like, okay, well, I happen to draw this element on the side facing us. If I had drawn that on the top of the beam, you'd get stresses in a different direction. So we're going to have to worry about that. But for now, I mean, intuitively, to think about this, what's going to be helpful is to think about what happens to like a rectangle you draw on the surface that's facing, out on the positive z side. Okay. All right. Well, the stress. So let's start first with circular cross sections. And we are going to use a formula that says tau, and I'm going to call this capital XY. This is going to be a temporary coordinate system, is equal to negative internal torque times rho divided by what's called the polar moment of inertia. So this rho is the distance from the centroid to the desired point. And this I sub p is called the polar moment of inertia. It's like a resistance to twisting. So I guess let's call it a geometric resistance to twisting. So just like the area moment of inertia is a geometric resistance to bending, this is just the same kind of idea, but it resists this shape twisting. And I have to define, so this xy is a temporary coordinate system where, with the capital Z axis pointing from the centroid to the desired point. Okay, so there's our definition when we have a round cross-section. The polar moment of inertia has an integral definition that I'll just give you, but we're never going to use it one single time. So the definition is the integral from the inner radius to the outer radius, in case you have a hollow shape, of rho squared times dA. And this rho is the distance from the centroid to your infinitesimal area dA. So you have it in your notes, but never look at that again. What you need to know is if you have a solid circular cross section, then I sub p, the polar moment of inertia, is pi r squared over 2. And if you have a hollow circular cross section, then the polar moment of inertia is pi over 2 times the quantity r outer squared minus r inner squared. Okay, so now how do we deal with this capital XYZ coordinate system? So this is the temporary capital X, capital Y, capital Z coordinate system. So let's think about a case where we want to calculate the stress at a point here. Okay. And in order to make this stress tensor add with our stress tensors for bending moment, tension compression, shear force, in order for this to make any sense, we eventually need to end up at a coordinate system where X is coming out towards us, Y is up, and Z is this way. But the way we're going to do that is we are going to first do the calculation in a temporary coordinate system where capital Y, our temporary Y axis, is this way. Sorry, that's not Y, that's Z. Sorry, I messed up your notes. And then your Y has to be this way, just so it's a rotated version. Okay. And then you have to figure out the angle that you have to go from your temporary to get to the one you want. This is your theta. So you'll first calculate the stress tensor in your X, Y, Z capital coordinate system. Second, you'll find the counterclockwise angle theta. And this is going to be about the x-axis. To go from the temporary, from capital X, capital Y, capital Z, to the one we want in the lowercase. In this case, the way I have it drawn, that would be sort of like maybe a positive 120 or 130 degree rotation to go from the red coordinate system to the green coordinate system. And now what do you do? Exactly. So now we'll say our Q is, these are always going to be rotations about the x-axis. So it's going to be 1, 0, 0, 0, cosine theta, sine theta, 0, negative sine theta, cosine theta. And then we'll just go the stress tensor we want is Q times our temporary stress tensor times Q transpose. This will make more sense once we've done some problems, but right now, does anybody have any questions about it? Other than that, it's really just plugging in formulas. So let's do an example. Let's say that we have a cantilever beam with a circular cross section, and let's just say we have a torque of 4,000 Newton meters. And let's say that the radius of this is 0.05 meters. And let's say what we want to find is, if this is the cross section, let's calculate first the stress here. And then second, let's calculate it here, halfway between the centroid and the top. So we want to calculate the stress tensor at A, and then we want to calculate the stress tensor at B. All right. Anybody just off the top of your head, do you know what the internal torque is going to be? We can calculate it. So, if you happen to just be able to say like, oh, it's got to be this, that's great. If you can't see that right away, no problem. You have plenty of time to do these. So let's just calculate what?
Just be negative 4,000.
It's going to be positive 4,000. Yeah, because and the way that works is to calculate the external torque, there's going to have to be a 4,000 negative to counteract this. And then when we do our cut, since there's a negative 4,000 on the left end.
Oh, you need a 4,000.
Yeah, that's right. But let's just do the calculation like we always have. So I'll start with a free body diagram of the whole thing. So we have a 4,000 here. We have a reaction torque here. We'll do our rotational Newton's second law about the x-axis. And so we have TR plus 4,000 is equal to 0. And so TR is equal to negative 4,000. And now we only need one cut. So X is, I didn't even say how long this is. Whole length. And so we have our 4,000 this way, our internal torque this way, rotational Newton's second law about the x-axis says negative 4,000 plus t is equal to 0. So the internal torque is positive 4,000. And this internal torque is what we're going to use in this calculation here, the boxed calculation. Okay, so first we'll do it for A. So we want to do it right at this point here. Our temporary coordinate system, remember our temporary coordinate system always has our temporary z-axis pointing from the centroid right out to the point we want. In that case, our temporary is our permanent one. Like this would be our temporary coordinate system. Are you with me on that? And so we're not going to have to worry about rotation matrices for this.
If the z-axis, you always want going towards the point.
Yeah, from the centroid to the point. Yep. And so our tau xy is equal to negative. I guess I'll just write the formula first, but the internal torque times the distance from the centroid to the point we care about, divided by our polar moment of inertia. And let's fill these values in. So our internal torque is positive 4,000. Our rho, we're all the way out at we're one radius away from the centroid. So that was 0.05 meters. And then our polar moment of inertia, just use the formula that I just gave you. This is pi over 2 times the radius to the 4th power, right? No. Let me just make sure this is right.
On the test, are you gonna label which one is which, or you gonna like you're gonna be like this one's for like solid circular cross section?
Well, I mean, I'll tell you. Oh, I see what you mean. It's pretty obvious. Only one of them has an inner and an outer radius. So that one has to be the hollow one.
No, I mean for like all of them. Like, cause like we're finding like for the area of the cross or
The area moment of inertia.
Yeah.
That one doesn't have a sub p, so I will list
Okay.
the one's polar and the one without a p is the area moment of inertia. And I did give these to you wrong. These should be to the 4th power. That has to be true because if you look at the integral definition, you have meters squared here, another meter squared here. So we have to end up in units of meters to the 4th. Okay, so pi over 2 times the quantity 0.05 to the 4th power. So that is 9.818 times 10 to the minus 6th meters to the 4th. And now we have everything we need. So our tau xy is equal to negative of 4,000 times 0.05 divided by 9.818 times 10 to the minus 6. And you get negative 2.04 times 10 to the 7th pascals. So the stress tensor at that point is 0, negative 2.04 times 10 to the 7, 0. Stress tensor has to be symmetric, so another 2.04 times 10 to the 7, 0, 0, zeros. Any questions about that? All right, so now we're going to part B. And on part B, we're going to have to use the temporary coordinate system in the rotation matrix. Okay, so for part B, we want the stress tensor at this point. And so our temporary coordinate system is going to have capital Z that way. And that means capital Y has to be this way. The permanent X and the temporary X are always in the same direction, coming right out towards us. So we don't have to change that. All right, so this time our temporary tau x, y is equal to negative torque times rho divided by I sub p. Our torque is still positive 4,000. Our polar moment of inertia, that just depends on the cross section itself. So that's the same as it was before, 9.818 times 10 to the minus 6 meters to the fourth. And this time, what's our rho? Yeah. So the whole radius is 0.05. This is half of that, so 0.025. And so the temporary tau xy is negative of 4,000 times 0.025 divided by 9.818 times 10 to the minus 6. And this is just going to come out half of what we got before. So 1.02 times 10 to the 7 pascals. And so if we want this in a temporary stress tensor, this would be our XY shear stress. So 0, I left out the negative. 0, negative 1.02 times 10 to the 7, 0, negative 1.02 times 10 to the 7, and then zeros for all the rest. But now this time we have to mess with the coordinate systems. Okay, so our temporary coordinate system was this. And the coordinate system we want to finally arrive at is this. We know this is a rotation about the x-axis. What rotation does that have to be? Positive 90 degrees, yep. Counterclockwise 90 degrees. So our rotation matrix is 1, 0, 0. Then 0, cosine of 90 is 1. Sine of 90 is 0. Negative sine of 90 is 0. Cosine of 90 is 1. Something didn't work here. Cosine. Oh, because I did it backwards. So cosine of 90 is 0. Sine of 90 is 1. Negative sine of 90 is negative 1. Cosine is 0. Why did I know my matrix with all ones down the main diagonal and zeros everywhere else is wrong? You know what you get if you multiply. That matrix has a name. It's called the identity matrix, and it just gives you back whatever you got. So if that's your rotation matrix, it's not going to change anything. Okay, and now finally, our stress tensor is equal to Q times our temporary stress tensor times Q transpose. And let's punch that. 0, 0, 1.02 times 10 to the 7, 0, 0, 0, 1.02 times 10 to the 7, 0, 0. So we just move those values around in this matrix. Does that make sense? Okay, so to make sense out of this, we have to do some kind of physical thinking about what's going on. Okay, so let's think. So does this make sense? Well, let's think about this beam from the top. So this time our coordinate system, x is going this way, y is coming out towards us, and z is going down. Okay? And the point where we want to calculate the stress this time is up here. Well, if we apply a positive torque to this, so we twist this end this way, and by the right-hand rule, that means twisting it like this. This stress element is going to change shape like this, which requires stresses here, 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 and here. And think about what those shear stresses are. The one that's pointing down is on the positive x face in the positive z direction. You see that? And so we would expect to have an xz stress that's positive, and that's what we got. What do you think happens if these aren't 90-degree angles? Like, say that we wanted a point that was off at 12.6 degrees. What would you guess is going to happen when you apply those rotation matrices?
We have one that's for the line.
Yeah, you just won't have like all of your x, y, and your xz shear stresses are all going to have values, and depending on what that angle is, those ratios will change. And now this example, the only external loads we had were torques, so we didn't have any stress due to shear force, stress due to bending moment, stress due to tension compression. But once you get to this point, if you did have those other internal loads, you would just add this to your list of stress tensors that you add to get the total stress tensor. Okay. Any questions? Okay, let's stop there. And next time we'll do another example, and then we'll go on to the thin-walled tubes calculations.
Wait, is this stuff going to be on that has some?
Nope.
No.
Yes. Sorry, this stuff is going to be on the test. Yes, this is the end of the stuff on the test.